This section deals with normal distribution. Just as an introduction, in general, if you have quantitative variables, so that's variables with numbers, such as heights and weights or scores, those are all type quantitative variables. First of all, you should plot your data. And we've learned a couple of different ways of plotting that data. This section, we're going to learn yet another way. Look for overall pattern and any deviations from that, such as the outliers, so data that doesn't seem to fit with the others. We're going to calculate numerical summaries, so just calculations about the data set that will describe it, such as we've talked about mean, median, mode, some of those things. And then sometimes you'll find that the overall pattern is so regular we can describe it by a smooth curve. And that's what's going to happen today with density curves. So a density curve is a curve, obviously, that is always on or above the horizontal axes, and the area underneath it is exactly 1. I want to talk a little bit about the area exactly 1 on the curves that we're dealing with today, because we're dealing with data sets or populations of people or other objects. The 1 is actually representative like 100%. So think of it in terms of decimal. 1.0 would become 100% in decimal notation. It does describe the overall pattern of a distribution. And the one that we have here, this figure 1.3 from your textbook, this is a picture of what we'd call a normal curve. It is a bell-shaped curve, so if you've ever heard of teachers say, I'm using a bell curve, this is similar to what they're talking about. The most of the data falls in the middle range with less on either side. Down here, if we start to talk about the median of a density curve, the median is the equal points area. So if I were to take and cut it in half and it represented the middle numbers, so the median, remember the median, what did we do? We found of the data set, we found the number exactly in the middle. Each area is the same. The mean, which before we were talking with just data sets, is the average is another term for mean. In this case, mean is the balance point. So if this were a solid material, like made out of rock or cement or some other solid material, if you wanted to, we could even make it jello. If we were to put this on a scale with a fulcrum point, so you see these triangles down here, if we were to put it on that and put the mass above it, it would be balanced. So notice right here, this green line on all of them is the mean. So if I put fulcrum here, obviously there's more weight to the left, so it's going to fall to the left. If I move it over here, there's more weight here to the right, so it's going to fall. Whereas if I put it right at wherever that mean is, it's going to be balanced. So it's going to balance itself. Think of a teeter-totter would be a good way of having a visual of that. So today's we're going to be working with the normal curve or normal distribution. So the normal distribution is a bell-shaped curve that is symmetric about the mean. And it does have a couple of rules with it. So first of all, if our mean, these are the Greek letters, so our symbol for our mean and our standard deviation. If we take and add 1 standard deviation from the mean and subtract 1 standard deviation from the mean, then 68% of the observations are going to fall in that area. So let's take our example here and let's start to work with these numbers. So on ours data set, we have, I got data from the ACT and of the 2001 graduating class. On the ACT, they did have a national average score of 21.0. So we have our horizontal line here. I'm just going to do a mark. So our mean here is in the middle, and this was 21.0. So that's our middle score. Now, if we were to add one standard deviation to that, I would end up over here. So 21 plus 4.7 is 25.7. And if I subtract that, it'd be 16.3. So if I'm looking at just explaining this data, another way of wording this is 68% of the test takers had scores between 16.3 and 25.7. Now, obviously, when you get your ACT score, they aren't giving you decimal scores, but this is, remember, representative of the national average. Now, the next one out says 95% of the observations fall within 2 standard deviations of the mean. So essentially all that I'm going to do is add another 4.7. Let's change this color. And subtract another 4.7. I'm going to change these colors as well, so kind of have pattern going on. So now if we're looking at these numbers, we can say this. So 95% of the test takers had scores between 11.6 and 30.4. And then our next one, 99.7, which is almost 100%, is within 3 standard deviations. So we add a 4.7. And get the 51.1. Oops, I can read that. And if I subtract it, .9. So then 99.7% of the test takers had scores between 6.9 and 35.1. Okay, we can use this information actually to make some more conclusions about the percentages. So we can talk also about those that are on either side. Let's put a bell curve as best I can. Imagine that's a nice pretty curve. So this is our representative of our curve, and if you want to, you could do lines at each of these. Okay, so let's talk about the 68%. So if 68% is in the middle, and the whole thing represents 100, 100 minus 68 is 32. So that would leave really 16% on either side. So 16 plus the 68 plus the 16 is 100. So we could also say then, we can make a few more conclusions. 16% had scores over 25.7, and 16% had scores below the 16.3. We can do the same idea with the 95%. So if 95 is in the middle, that 95 and 100 have a 5% difference. So that means there are 2.5% on either side. I'm gonna kind of draw here. So 2.5 plus 95 plus 2.5 is 100. So then we could also say then 2.5% had scores over 30.4 and under, no, and 2.5% had scores under the 11.6. Then we could do the same with our green here. If we do 100 minus 99.7, that leaves only 0.3%, so that means 0.15%, not a very large group, had scores over 35.1, and 0.15% had scores under 6.9, which those numbers should make sense to you. High score is a 36, so it'd be logical that not many students get a perfect score. So you can use the 68, 95, 99.7 rule to determine numbers like these. But let's say we wanted to know, well, how many students get a score that isn't one of these? So instead of, maybe we want to know how many students get a score over 22. We have a guess. We know that 16 go over 25, so we know it's going to be a little bit more than that. But using this model, the 68, 95, 99.7 rule, we can only really get an estimate. So we need to talk about a Z-score, which is going to help us determine the likelihood or the probability of a score falling in a different range that doesn't fit in the 68, 95, 99.7 rule. So X is our observation, so that's the number that we're looking for. We're going to use that. Our mean and our standard deviation, we get a Z-score, a standardized value, given by taking the value, the observation, the X, minus the mean, and divided by the standard deviation. Another way of writing that, instead of writing out in terms, is you can write it in a notation that is capital or N, so normal distribution, with the mean and the standard deviation, and then talk about the variable X. The formula is the same, no matter which way that you write it. So whether you're giving information in a formula type model or just given in a straight sentence, you can use the same exact formula. So this is our formula that we need for all of these. So we're going to use this formula. So let's go to our information, and we have our graduating class, again, same average and same standard deviation, but we want to know what percentage of the class had a score below 19. So what we first need to do is determine our Z. So Z equals our number 19 minus the average divided by the standard deviation. And this equals, you can calculate that on your calculator, negative 0.426. So this is not of the percentage, obviously it's a negative number. So what we need to do is go to what is called the Z table, or the for the normal curve. So this is in your back of your book, it's table A. In the back of your book, you might want to mark that page. If you also, I do have extra copies if you would like a copy. So what we're going to do is there's numbers here going down the left side of both. This is just the table continued. And then numbers going out. Those are representative of the decimal. So our number was negative 4.26. So I'm going to go to negative 0.4. So we're going to talk about this row. And then it was 0.426. So you could go to, so 0.42 is column is here, 4.3 column is here. So we really should be talking about both of these numbers because 426 is in between those. So I know they're kind of hard to read, but this one is 0.3372. This one over here is 0.3336. So let's talk about what those mean. Let's start with this first one. So the 0.3372 really represents 33.72%. And then this one is 33.36%. Since our number is directly in between those, we should find the average of the two. So if I add those together and divide by 2, so from my Z table, I get 33.54 on the Z table, which is 33, I'm going to type it. So it's 33.54% is our final answer. So we're going to do this a few more times, but what we just found then is 33.54% of the class had scores above 19. Or I'm sorry, below 19. Now we're going to find the scores above 19. So the whole chart, I'm talking now, let's focus in on this area up here. This part of, when you find the numbers, it is finding the areas underneath the curve. So it's the shaded area. So we found the areas below. So this one we can also call it like the tail on this side. So we found the area below. So if we want to know, well, how much then is over here on the other side? So we're talking about this area. And the whole thing is 100. Wouldn't we really just take the 100% minus the 33%? Or in decimal, we would take the 1 minus the 0.3354 to get 0.6646, which is 66.46%. So let's do another one. Let's do 16, so below 16. So we first, again, just repeat the process. We have to find our Z using the formula on top, which is take your X minus your mean divided by your standard deviation. And we get negative 1.06 for this one. So then we need to go to our Z table. And this time we're at negative 1.06. So I go to negative 1.0 and then go over to the decimal place of 0.6. And my number here is 0.1146. So I can remember that. So it's 0.1146. I don't think that's right. Let's look back. 0.4446. Okay. Or 14.46%. There we go. So approximately 14% of the class of 2001 has scores below 16. So above 16, again, that's below, the whole thing represents 1 or 100. So if I do 1 minus 0.1446, and that would be 85.54%. So now if I'm looking for those that are between 16 and 19, let's talk about this a little bit graphically. So we have our normal curve as best as I can, and we have 16 about there, and 19 is about here. Remember that mean was 21, so 21 here is here in the middle. And we're trying to find this area in between. We have a few numbers here that are going to help us. Our first one that's going to help us is we know below 19 was 33.54%, and we know below 16 was 14.46%. So then couldn't we really just take, well, below 19 is that, and take away the people that are below the 16, we'd be left with the people in between, which is 19.08%. Okay, one last thing, we can also use this Z-score and the Z-table to figure out how high or what a score a student needs to have in order to fall into a certain group. So this one, we want to know, well, how many are going to fall in the top 3% of the scores? There's a couple ways that we can talk about this. Note the z-tables are equal, so what's on one side, this lower end and the upper end are the same. So we know that 3% is 0.03 in decimal form. So remember, we would have gotten that from our z-table. So we're going to go back to our z-table, and this time we're going to find that number in the inside. So we're looking for 0.03 inside our table. So I'm in here 21, 20, 27, 26. Oh, right here. It's too many. So make sure you go to your table. 0.030. We'll go with this one's the closest one. So if I go from there and I'm going to go out. So I can draw our straight line here. So the z-score then would have been negative 1.88. So the z was negative 1.88 was our z. So let's set up our formula. We know it is x minus the average, or the mean, divided by the standard deviation. It's equal to the z-score. So if I calculate that, so take the negative 1.88 times 4.7 plus 21, I get an x value of 12.164. So if we're looking at the table, that really means the top 3%. So if we use those numbers as they are, try that again. Make my curve as best I can. The top 3% have to get a score above the 12 point something. That doesn't make sense. Now remember though, I just said that this end would be the same. So maybe if we approach this problem a little bit differently, so this is really the bottom 3% is 12 or higher. Now if you know your upper end, it's going to help, but let's redo it. Top 3%. Remember, your z-table is always going to give you values that are less than that. So if it's 3% above, we can work with, there's 97 below, right? So now if I go to my z-table with 0.97, and I would use this one. Notice that gives me the same, get it lined up, 1.88, but positive this time. So my z is 0.188. So if it's a positive, then I have x minus 21 divided by 4.7 equals 1.88. So if I take 1.88 times the 4.7 and then add 21, I get an x value of 29.836, which makes a lot more sense to it than the 12. So now if we're looking at this graphically, this is the 29.836. So make sure when they're talking for the top percentage that you either consider, you can do it with that percentage, but remember that's going to be for the below. So you can either change your z to the opposite sign. So if it's negative, you can make it positive. Or you can just calculate it with the percentage. And the reason why that works is because when you're looking at this normal curve, let me go to a better picture. The area underneath each end is reflective, or it's a mirror image. It's symmetrical around the mean.